Hello and welcome back to a new video here on the Ludwig Fusel channel. Today we're gonna talk about the mighty feature of C++ called templates. Now, in the last video we have moved our code into multiple files. Prior to that we have written classes and everything was nice, easy, flexible, nice to use and reusable, right? And today, it's going to be my task to show you that it was not reusable, what we have written. Well, it's going to be quite simple how I'm going to show you how our code was not reusable. We're going to today write a class called vector. A simple class called vector. So, class vector. Now, actually, let's call this vector2 because I don't want to get a hassle into writing some big vector stuff. Now, vector2 shall operate on floating point values. We haven't talked about floating point values yet, but floating point values are just values with fraction values, right? IEC fraction values, floating point values 0.2, something like that. Floating point values come into flavors, float and double. Double has a double of the position of a float, so double of digits. I think float is 32-bit and double is 64-bit. So float and double just the matter of position, especially if you want to go to the GPU and you're doing graphics programming, you're always going to use float because the GPU is actually a 32-bit processor. It might be able to do double position ops, but in general the GPU is 32-bit, so we're going to use float. Now a vector has two components, so in this case we have the component x and the component y. I do just want to initialize them to 0. You can do float initializations like that. However, float are fraction point numbers. So what you always want to do, append is a point dot. However, a point dot, if you have an over that is a double, and if you want to indicate it's a float, you're just going to write a f to indicate that's a floating point value, and it's going to be a float. You can also capitalize this, but that's just how I do it. So yeah, this is just going to be our two component vector with x and y. Now, what I want to implement for this vector is a printing operation very quickly. So an std ostream reference operator shift, and the operator shift is gonna get the std ostream reference os and a const vector 2 reference vector, not percentage reference vector, and then it do some stuff. We first need to be able to access these. Actually, what we could do is we could just make x and y public, which would actually make this more of a struct than a class, but I'm just going to keep it as a class for now. And this now basically allows us access to x and y because it should also be possible to modify x and y. So I'm just going to make this all public here, even this is not like really, I wouldn't love to see this on a class. So let's maybe actually do this as a struct. I'm struggling with that, seeing this as a class. So this would be a bit more telling what it is, something like that. I mean, structs and classes, I told you, still be exchangeable. Now for printing, this is just going to be quite simple. I am just going to write this how I learned this in math. So open up a bracket, then writing the x value, writing a comma and a space, writing the y value, and closing this up again by closing the bracket. So this is how I learned to write vectors, at least if I'm writing them inline. So we want to do it here as well. We should be able to print these. Now we could do a quick test and see if this would work by providing some printing. So let's do a simple vector print here. So I want to print a vector. Now this is also a syntax that you don't know yet. You can actually construct a vector or a struct or a general class with all the values in it by using the curly brackets. These curly brackets after the vector like that means that you want to initialize it, and you can initialize this by giving the values in order. So we have x and y in the order, so I could do like 1 and 2 to have a vector of 1 and 2, and that should be automatically converted to a floating point and to a vector because I gave it the values. Oh yeah, we forgot here to return a value, so let's return OS again, and let's try this out now. Now these should be automatically converted to float and be printed. They are not. That's interesting. Why are they not printed? I'm not even getting the print of the vector here. Of course, above here is it. So our console is again bitchy. Let's try to, did I close it up? What is that one? Yeah, that is a different one. If I run this now, we should get it properly. All right, so now you can see we get our vector double point and then 1.2, so you can see this works, and actually this looks like that these are ints, but this is just because we are printing floats and they don't have any fraction part. If I would do something like .2 or .3, something like that, or even like 3, 4 to make this look a bit more interesting. If I would do this like that, you should automatically also see that we get the fractions behind there. So 1.2, 3.4. So you can see that this kind of works. All right, so if we have a vector, we of course want to do math with them. So what I could do is I could try to add and multiply vectors. I'm not going to do proper vector multiplication. These are just going to be per component multiplications, but you should get the point. So what you can do is you can do an auto vector 2. Let's call this v1 for the first vector of 2 components, and let's maybe say 2 and 7 should be in here. Actually, the fraction values were nice enough as well. And then I could like do a vector 2, and the vector 2 would be something like, let's say 3.8 and 1.6. And now what I want to do is I want to have a vector 2 a result 1, and the result 1 should be vector 1 plus vector 2, which currently doesn't work. And this another result would be maybe like, let's say, subtraction is something that I want to do, and I also want to do multiplication, so vector 1 times vector 2, something like that. But as you can see, this currently doesn't work, and to solve this, again, operator overloading. We already talked about these. So if you want to add 2 vectors together, we can do this in multiple ways. One way of adding a vector together would be to define this out of the class. So you could do this like that one. So you could do like a vector that, operator plus, and you could do like a const vector reference left-hand side and a const vector to reference right-hand side. And if I would add this like that, you could see that the plus operator would work, and we can do this. However, I personally like to have as much encapsulated in my class as possible, which is why I like to put this into the class itself. And if you do this in the class itself, you're always going to get the right-hand side, and the left-hand side is like the current one itself. So what we really would construct is we would construct a new vector out of that, and we would basically do x plus RHSX and y plus RHSY. So we take our own y value and add the right hand side's x to that, and the same one here. We are not modifying our own class, which is also why this could be actually const, this operator, because we are not modifying it. So this is a operator that's not modifying ourselves, so this should be const, and you kind of like get the point. If I copy this over for minus, it's gonna work, and if I'm gonna copy this over for multiply, it should also work. Multiply, and now if I do that, the code down here should look good. And let's do AC out quickly, SCDC out. So let's say the vector 1, or let's just print out v1 completely. So like v1, and then we have like v2, and we have v2. Let's do an SCD handle, and then we can do an SCDC out and print all the results in here. So let's do a result 1, a result 2, and a result 3 here, no, R3. Let's do an SCD handle here, and let's see what we got if I run this code. It should, in theory, try to convert them. So you can see 1.2, 3.8. If I add them together, we get a vector of 5, 5. If we subtract them, oh, this doesn't seem right. There should be a negative number. Yeah, ready the, why? Why is subtracting not working? Interesting. Let me quickly think about that. Why is R2 0.0? Like multiply, this seems to be legit, but did I? Oh, okay. Of course I need to subtract vector 1 from vector 2. If I don't do it, it's good. And also, like, we get a few warnings because this one were no floats. So if I explicitly do floats, you also don't get compiler warnings. Don't know if you saw them, but that's like the idea. Oh, and again, I screwed it up. here, like that one, minus 2.6, 1.8. Now we're at the point. Now you can see that our vectors work and our arithmetic works. By the way, actually what you can do, if you already know the return type, something like that, you know that this is going to be a vector, you can actually in C++ call this one auto. And if you write an auto, it's going to automatically deduce the type, right? That works actually quite well, and you don't need to type out the vector all the time. I tend to avoid auto when I'm teaching somebody C++ because you're never going to really know what auto is. In this case, if you hover over that, you can see this struct vector2, because you can see it's a operation between two vectors, which is defined here, which results in vector. This is why this is actually working. And the idea behind this, you can see like it's automatically using this as vector because we directly initialize these as vectors. If we would do something like that, it wouldn't work because it now can no longer deduce what that one is. This is now a std initializer list, whatever that is. If I would define that one like as a vector2, you can see that it actually works. So in this case, something like that would totally work, and then the operations here would work, or we can use auto here. So it really depends. You need to have this at least one time, either here or on the other side, to initialize these. This is just how C++ rolls. Oh, damn it. So yeah, so you can see like all of our vector arithmetics work. And why am I doing this? Well, I am doing this because I want to show you how bad our code is. Like vector stuff, all working, all good, tested, nice, works. Now, let's see how we go if we are trying to pre-compute vector values. So I'm going to have a vector2 function. How did the function look like? I quickly need to peek how this was looking. So yeah, we had an x value here. So we had a vector which was like, let's call this like generate vector, and we were generating the vector depending on the x value here. Now, how do we generate vectors out of an x value? Well, could be simple. We could do something and return something like x. This can be converted to float. It's no problem. And x times 2, something like that. Can you convert this to no conversion from int to float, but if we do this like that, it should try it. Why can't we convert to float? I mean, we can convert to float. I know that this works if we do it like that. Let's try this out. Or what you could also do is you could define that one as a float, and if you're multiplying a float by an integer, it's giving you a float. So this would work. You could also like convert this by multiplying this by 1.f. So you don't need to specify 0 here, by the way. You can actually also do like .0. This also works. But in this case, like 1.f. So yeah, this would be a function that generates our vector. That's quite nice. And with this function generate vector, I now want to pre-compute the functions here. Now I want to use my function pre-compute to pre-compute these. And what you're going to notice is that this will not work. If I try to get a function precacher out of that with like an x, a count, and this function, you can see that it no longer works. Why is it no longer working? Well, because vector2 is not the type that we are using. If you're recalling our function precacher, you can see that our function precacher, if we uncollapse it here, is using 32-bit values, 32-bit integers. 32-bit integers here, size of 32-bit integers, 32-bit integers in as a return value to our function. It's always using 32-bit integers in 32T. And that's bad, because we cannot even do 64-bit integers. If we would have a function which does 64-bit integers, and 64T F2, like something like that, F2 in 32TX. I mean, I'd like the X is 32-bit, but yeah, if we would have a function like that, not even that one would work. Only 32-bit numbers work. Only as soon as this is going to get 32-bit, it's going to work. And this is something that we want to avoid. We want to avoid writing bad code like that. We want to write flexible code. We want to write flexible code that can depend on how we want to use it. Now, one idea would be to completely copy paste the class and replace in32T with vector2 or in 64T. But as you can see, this is not a good idea. Every time we are creating like a function precacher, we need to copy and paste the code. No, this doesn't work. You know me, I hate code duplication. Now, an idea would be to use insert2t as a variable. However, this doesn't work in C++. This would maybe work in Python, because Python, it's a non-type language. On Python, you just have objects, and you can just multiply objects, and if objects can be multiplied together, everything works. If they can't be multiplied together, it fails. But Python has many drawbacks that I don't want to address here, because it's slow, interpreted, and I hate the syntax, but that's a personal topic. But we want to use C++, right? But we also want to use variables on types. And actually, as you can see, this doesn't work. I cannot use something like type x equals int. I can use something like that. This doesn't work, because types don't work like that. Types are a non-existing construct. Everything in the end is going to be memory, raw memory, and the types need to be known at compile time. And the compiler need to know the types so that it can generate the code based on that. So actually, there is no way to write one class and one binary code for multiple types. This doesn't work in C++. But what you can do is you can tell the compiler to automatically generate another version of your code depending on the type that you give it. So actually what works is that you give the compiler a kind of compile time variable type. Now, we're going to do this in a second, but we're going to do this on a way more simpler example so that we can get started here. One important thing is that this all needs to be known at compile time. It's not possible that you get this later. It's all required in compile time. So before we do this on the class, let's start and do this simple on a function. Let's imagine a function type sum type A, type B. Just a simple function, and the idea of that function is to return A plus B. However, we need to now find a way to replace this type as a variable. Now, we can't really use a normal variable, but what we can use is we can mark this function as a template. And by marking this function as a template, we basically tell the compiler, hey, this is a copy and paste template. This template can be reusable. So what we tell the compiler is that this function is a template. And we do this by writing templates above the line that shall be the template. Now you can see if we are typing templates, things even get worse. Now the compiler doesn't know anything. Well, this is because the template doesn't have parameters. Now the template is not a function. You can't do this like a function. Actually, for the template, we have reserved these pointy brackets. And if you're doing this like that, you are basically giving the template some parameters. It's just a different syntax, just a different bracket here to tell it what we're doing. And now what we want to do is we want to now specify this type as a variable. Now this doesn't work like a var type. Doesn't work like that. Now actually what this type is it's going to be the name of a type. So what type do we want to use? The name of the type could be int, float, int32t, int64t. So we want to have the name of the type. So we declare this as type name type, and as you can see, as soon as I finish that, boom, it works. Ha! Very simple. Type now here is recognized as a type, but this type is now dynamic, or compile time dynamic. Not really dynamic, it's need to be known as compile time, but it is dynamic. You can see we have the type here, and it seems like the type would be a type. But really what the type is, it is a template parameter of type name. So it's going to be any type. So type is later on by the compiler being copy-pasted with the actual type name that you're going to give the template. Now, how can we use this template? Well, it's actually quite simple. You can just use it by using the function sum. You can use like an int x equals 0 and y equals 5, and you can just say auto result equals sum of x and y. This works because the compiler actually sees, okay, x is an int, y is an integer. Well, I can match this with int and int and int. I can match this to the type name int. And as you can see, this would work. We can also do this with float. We can also do like a fx to 0.f and a fy equals to 1.f. We can do this here as well. Then we can do an auto result of sum of fx and fy. This would also work, and well, everything would be good. However, yeah, let's actually show you how that actually works. Let's make a breakpoint here. I was intending to put a breakpoint in here. Okay, we have multiple times result. That is an issue. Where do we have result again? Oh yeah, okay. Yeah. Let's just call it R1 and R2, and let's see if this works. Now, in32t redefinition. Ah, okay. Aha, yeah, and let's call this ix and iy. ix and iy. Okay. But we do that here, you can actually see that if we start 5 and 5, you can see that it worked. We get a result 1 of 5 and a result 2 of 1.0. The one result is a float, the other one is an integer. And we were kind of like able to write one function that could be used by multiple types. Very simple, very easy, very nice. Does work, say very, very easy. However, you can have issues by using functions like that. You could have an issue if you would have something like a in64 TS4I, so the 64-bit integer, which is 5. And what you're then going to do is like you do an auto R3 equals sum of S4I and 2. If you would do something like that, it wouldn't work. Why does it not work? Well, because it cannot really deduce the types automatically. You can see that it tries to find a function that takes an insert, an int64t and an int. However, we do not have a function take these. These types are both the same. You could solve this by adding multiple. You could do something like type 1 and type 2. Then you would do something like, okay, I'm going to return a type 1, I'm going to take a type 1, and I'm going to take a type 2. If you do something like that, this would work again. However, really, it's now, the return value is now dependent on the second type. So if I would do something like 2 and that, the 64-bit integer would be truncated to a normal int, which is something that you probably don't want to do. So really what we do here in these cases is we just define one type. We're going to define one type, and on this type, this function is going to operate. This is just going to operate on that one single type. And instead of leaving it up to the compiler to decide what we use, we're going to explicitly tell it what to use. And you can do this by adding these pointy brackets after the function name. And if you add them here, you're basically going to specify the type variables of the function. So if I write an int64t, you're going to see that the 2 gets converted to a 64-bit int before the computation is done, and we all have 64-bit integers here in this case. So this is kind of like the signature of the template, with all the variables in here, for example, like for summing the types. And here we can specify the parameter. We define a parameter for that function, for the template, and what the compiler is in the background, the compiler is really generating multiple versions of that function. Really what it is doing is that it compiles the function multiple times with different types. But for us, it's no code duplication. It is like copy and paste for the compiler, but it's all handled by the compiler. We don't care if the compiler copy pastes. We just care about our code being clean and fast, and it's still going to be fast even if we have a bit bigger binary with multiple functions, of course. Now, this of course also works differently. You can of course also like say, I want to now fold xi and fx, something like that. If I want to fold these two together, it's of course also not going to work because I can't deduce them. Now I can say, all right, I want to have the result as a float, and then the integer is going to be converted to a float first. Or you can say, all right, no, I want to have 64-bit integers, so the float is converted to a 64-bit integer, the other normal integer is converted to a 64-bit integer, and the result is going to be a 32-bit integer, 64-bit integer. So really with functions, the deal is quite simple. Right, you're just going to define parameters and it works. Now, on classes, it works the same but different. On the classes, it is not actually that hard. You just need to be a bit more aware of what you're doing. So let's jump to the function Precache and let's make this a template. We're going to do this the same than we did this by functions, but now instead of giving the parameters to the function, we're going to give the template parameters to the complete class, which makes this whole class a template. Now, one important thing is that templates are always need to be declared in headers, at least if you're doing this with classes. Now, currently I've written this inside with the function with the C++, but this was fine because the compiler needs, the point behind that is that the compiler needs to be able to read the whole definition. The compiler requires all the code in the header because when we instantiate this template with a certain type, it needs to read everything. It's not possible that you do this, that you declare a template in the header and put the implementation in the C++ source file, because if the source file is compiled, it doesn't know which value the type is going to be. So it's not really like pre-compiling this with all types possible. That doesn't work. It would be going to infinity to compile this with all types in the world imaginable. If you have like 20 libraries with 20 types, and it wouldn't be practical. So the idea is if we are doing this with a class, with a function, if the function is not accessed outside of the C++ source file, if you just have something that's valid just in the C++ source file, everything is good. But as soon as you have something that shall be valid across multiple files, for example, we want to consume the function Precache in the simple C app, then all the code needs to be in the header if you're using templates. So again, here, template, which makes this whole class a template. Type name, because we want to name a type. And now what we commonly do is we call it T. Because the basic type, the general type, the type on which this function precacher works, the type for the precaching function, is T. T is the type of that function. And now things are going to be simple. We just need to replace T everywhere we used our type previously. So our values array, which hold the values, is no longer an int32 array. It is now a T array. Okay, so let's go on. Now we are memcopying the values over. Previously we used the size of int32t. Now we just want to use t. Now one important information, this can fall back because this is now no longer copying. Actually, if you want to do this correctly, you should do this with a loop. Let's actually do this for a loop, with a loop. So what you really would want to do is you would say, I think like, did we use a int32t for that? I think yes. You would really want to do something like that. So other.count I++, you would really want to do this in a loop instead of a memcopy, because now you can provide any type imaginable. And if this type is a class and this class has a custom copy function implemented, then this custom copy function is not called when you're memcopying, and it can give issues. So you really want to do custom copy here. So values at I equals other values at I to do a proper copy of that array of data, because again, this is calling the copy constructor, or the copy assignment. Actually, this is going to call copy assign, which is important. Here we are allocating them with new, which means that they are initialized to a like default constructed object, and then we use the copy to copy over from the other object. Important that you do it like that. If you don't do it like that, you can have issues. So that's something that you need to have in mind. If you're using templates, you need to be really curious and you need to be really aware of what you are doing, because everybody can implement everything. This just needs to be implemented. Like this needs to be like, if your function or if the class that you want to precache deletes the default constructor, this template will fall apart, because it cannot do this with new T because it tries to default construct them. If you don't provide a default constructor, if you delete this class, this template falls apart. It will not work for the type. Same here with assignment. If copy assign doesn't work, the template will fall apart and this will no longer work. But again, that's not something that we are too curious about now. Now let's scroll a bit down. These are all now copied correctly. Let's take a look at this one, function precacher, x and count. They are going to be the same ones. This is okay to have them as the same one. But now you can see that actually the return value of our function pointer, this return value shall now be actually t. Shall now be t. So that we get the right return value there as well. Everything else should be the same. Let's scroll a bit through that. And actually you can see you are no longer getting errors. As soon as you are using a template, you are not going to get IntelliSense. Templates are a bit more involving because they require an instantiation with a certain type. And it's no longer going to give you errors for IntelliSense. I think you can provide a sample template argument. If you do this, you can actually give it a sample here. You can, I think, click on this edit, and you can give it a template type here. So I could give it a type like, let's for example, let's give it an int64t, and if I'm going to give this an int64t, press enter and go out of that, it is going to give us IntelliSense, which might fall apart or might not fall apart at certain things. Why are you? Okay, no, you need to actually define it. Now, if I select int64t above here, you can see that it now tries to IntelliSense with int64t. And you can now see that we now get a bit of errors. You can see that we get an error here because the member internally is an int32t and we are allocating a new int64t. So here as well, the function pointers are not matching, but if we are going through our class and we make sure that everything is replaced, so we also put in t here, which is going to give us an error somewhere there. Should this give us an error here? We went through like, yeah, now we get the error here because it's not matching. Here also a different new, that's also important. That one is okay. We just need to scroll a bit through here to see where we got this. Okay, this is also correct. This one is wrong. We need to have a property here. Operator here. If we want to access it, we also want to access t. Now currently we are accessing by value, so now this should actually be a const reference now to get actually a reference to that. And if we want to copy that, we always have the option to copy it, but this should be a const reference of t now. And then down here we also need t, and there's a return value for the function pointer. We also want to have t, and if we change all of that, we should no longer get any IntelliSense errors here after we told it that we want to use 64-bit integers just for testing here, and everything should be fine actually, which looks good. And if we are now hopping to our simple app.cpp, you can actually see that magically this works. Now, one thing that I do want to do is I want to give this a name. Let's just call this one the VC for the vector container. And let's also do a VC compute here to compute all the values there. Now, if I run this, this should now already work, but might not. Okay. Okay. What do we have? All right, unknown size. Okay, so right. The issue that we're gonna have now is that our print function down here falls apart because our print function down here is no longer working. You can see this is no longer working because it is a template. And if we want to print this, we would need to define a template here. For example, int. If we would supply an int here, this would work, and we would now be able to print precachers of an int. However, we want to print all precachers, and if we want to do this, it's quite simple. We just need to provide a template for that function as well, and the type name is going to be t, and then we're going to pass on t in here so that printing goes through. And if we do this like that, it fully works. Like this is always this, especially when you're using templates, you're going to get so many errors here, and you can see like the errors that I got here were not really telling us what's going on there, but we're gonna see. Okay, this is going to still fail. I actually wanted to go 2 steps ahead. Now this is actually going to fail because the Precache container is now falling apart. The Precache container is now falling apart because the Precache container uses the function precacher, and the function precacher is typed, and so we would need to either specify an argument here as well, or we need to define the actual content type. Now there are multiple ways now of doing that. Now again template type name t, very simple idea here, and then we can use t every time we use a function precache. But actually, is it? Let's do this. I think it is actually directly passing on t. This should, if it works, directly pass t to the function precacher. Not aware of that. Let's try this out. Of course, we need the template now down here as well. Template type name t for printing the Precache container. And in theory, if you have t and the arguments are named the same, this might actually work. No, it doesn't work. Okay. It's probably not working because we don't have provided as a sample argument. Let's edit this and let's give it also the insert 64T so that we can see a bit of debugging, and let's select the 64T version, and this should now give us errors again. Okay, so now what you could do is you could add T in here every time you use it. Function precacher T, come on. Get rid of your error. Yeah, it's gonna probably, now there it is. You can see this would work as well. What you can do alternatively is you can define yourself another type here. You can get another type name here and call this PC, because this is the precacher. And now instead of leaving this type open to the user, you're gonna actually assign an equal sign here, and you're gonna give this a default value. And you can just write function precacher, function, come on, function precacher based on t. This actually works because t is an argument before that. So you can use that argument that you have here as the default parameter for the second one. So you can basically define PC as a function precacher of type. Or you could also like PCT, something like that, or PCT precacher type. But I'm just going to call this PC here. And by default, it's going to assign this default value. So if you're defining something like int, then PC is going to be equal to function precache of int. And now what you can use is you can use your PC instead of always writing down what you got here. So you can select like const PC, PC move, PC add here as well, the shift operator with the PC, the array operator at the PC here, and then again the precaches down there. So you can just define them as PC, the precaches, and then they look a bit more cleaner. So I know that these are your precaches, and yeah, kind of like define what's going on here. This is now a bit more of advanced template stuff. Still, the sky is the limit. Templates are 1,000 times more powerful than what I have shown you here, but you should get the point on what's going on here. Now hopping back to our sample C app, you can actually see that this container is no longer going to work because now we actually need to define the insert32t that we use there for the functions. But if I use the insert32t here now instead, you can see that all of the code still works. Moving this like to a 64-bit integer is going to give us a fail on the shift operator because this is now a 32-bit one and the container is a 64-bit one. So we need to now here explicitly define what this is. But if you're doing the syntax like that, you can see that the code is not looking complicated. The code is looking for our basic old example. It's looking the same. But now it is more versatile. You can see that we stored vectors in here. And these vectors were only deduced by having the function pointer in here. Actually on this function pointer, because the function pointer returns a vector, it was able to match the type for the function precache, which when I hover over this is a vector. But getting back to all of that, putting a breakpoint in here and now hoping it all compiles. Let's see. Yeah, we compiled now. You can actually see now that our VC should have vectors pre-cached. So if I take a look at my PCs, you can see that this is a pointer to vectors, and you can see that we have the values of a vector, which is 5 and 10, because we are starting at 5, and we have 5 and the double of 5, or x and the double of x in our vector. So we have 5 and 10, and if we would take a look at this in a more of an array style, or we would just print it for starters, cout is still going to work here because we have templated the operator for cout as well. So it's going to be dynamically generated for the type that we have of precache. You're going to see that we have the f of 5 resulted in 510, the f of 10 resulted in 1020, the f of 15 resulted in 5030, the f of 20 resulted in 20 and 40, and the f of 25 resulted in 25 and 50. And you can even recall that even our operator for printing the vector is done correctly, because the function precache also uses shifting out. So in the print, where is it? It uses the shift operator of values, but since values is now the vector, it is now using the vector implementation of the operator here. So you can see that like all that code is magically adapting to that. And the idea behind that is that the code that you have here, the precache and the function, the containers, you do not need to change them. You just provide whatever you like. You provide the type that you like. You're going to give these in as template arguments if you use it here, because here we can't deduce it. We can't deduce it because the container is like, it needs to know what type it needs to store because we are not adding it here. So there we need to specify it. Here we have the function pointer, so it directly knows what's going on. And really what happens is you can write and input every function now. You can see generate vectors. If I would now go back to my int64t example, f2, int32tx, if I would go back to that example, even through not providing an implementation here, it just works out of the box. It just works out of the box. The templates in the background are generated all dynamically, and templates are such a powerful thing. But what I care is about my vectors, because I'm now like in love with my vector idea. So actually what we're going to do is we're going to make the vector going to be its own class or its own file, and we're going to then also show, and yeah, that's a good idea to make this in here. So let's maybe grab the vector out of there, and let's get the vector into my HBP, because I want to have it in my HBP. And a vector is going to be the function that we are dealing with, and the vector function now is going to be a quite nice function here actually. It's not going to call generate vector, but I do want to give me some headroom here. Why is the vector 2 not? Okay, because it's a simple app vector 2 now to make this work. But this again is something that should be in our header, because it's now the OStream operator, and then it's also going to be inline if it is in our header, so that we print it correctly. Now the only thing left to do is implement the fvector function. So let's create a few vectors. F. How did I call this now? Vector 2. So vector 2, and now I can like create a vector of x. Let's maybe, oh no, let's do this like, let's do a vector of float x. And to scale this vector, I'm gonna multiply this with another vector here that multiplies the first component by 1 and the second component by 2 to get like all the vector data in here. And why are you not working? Okay, because this, of course, needs to be now a vectorized function. But now you can see that we create these two vectors, we're going to multiply them with some smart values, and we can do vector arithmetics in our function, and our function really can look however we want to desire this, every C++ magic that we want to use. The only thing that's really required then now is to have this one properly as a vector 2 version of it. Now, why are you now having an issue? Because it's called a vector, okay. No, but I just want to call it f, right? Why no need to call this f vector? And as you can see, the only thing really left to do is to change the vector here, and everything is done dynamically. And now we actually have at one point actually changed the output of our application, because now we are pre-caching and printing vectors, which we haven't done previously, but we can, because C++ is our language, and in C++ we decide how our syntax look like. And I decided that this is how it should look. This is how we define the type that is generated for the function. Still, we again gonna give it a 32-bit x and a count to generate these, but you get the point, right? That's the whole idea of that whole stuff that we're here doing. My idea here is to be that the code looks like that. Everything else is like library code. This is library code, the function precacher, this is library code. Precacher container, this is all library code that we don't really care. That's all suited for our application needs. And in our application itself, we just quickly, in a few lines, defined ourselves our custom vector class. We have defined as our f, and we are pre-computing a few values based on user input. That's the whole point in templates, operator overloading, classes. You can define how things roll. You are the boss. You define how everything looks. It's your language, your code. You are the boss, you are the king, you are the ruler of your C++ application. It's your land, user land, and amazing. That's how we want to have it. And that's how simple stuff gets. And that's how, I don't know. And that's how complicated everything is behind the scenes. But hey, that's the whole point. Writing a class, putting your brain into writing your classes, and then just use them. Just reuse them, write simple code that looks nice, and everybody sees what's going on. Thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.